Okay, now for an example using the convolution. We have a function s over s squared plus 4 quantity squared. If we didn't have that squared on the bottom, then it would simply be a cosine of 2t. But by itself, it causes some issues. In fact, if we expanded this using partial fraction decomposition, we still would have the same issue of having a squared irreducible quadratic in the bottom. So what we're going to do instead is factor it into two pieces. We recognize the s over s squared plus 4, and I'll write that as s squared plus 2 squared. And then what's left over is a 1 over 2 s squared plus 2 squared, but we need a 2 there. So even though a 1 is left over, we need a 2 for our sine component. So I put a 2 there and pull a 1/2 out. And I have an inverse of a product of two transforms. One, which is the transform of cosine of 2t, and the other is a transform of sine of 2t. So I write my answer as the convolution of those two. 1/2 times the cosine of 2t convoluted with the sine of 2t. Now, because I can multiply these two in either order, it really doesn't matter what order you choose for your f and g. In this case, it's about as convenient either way. But there you have it. So we set up the integral from tau equals 0 up to t of f of tau. Well, f is our cosine, so that's a cosine of 2 tau. There's our f, and here is our g. G of t minus tau turns into a sine of 2 times t minus tau, and then we integrate over tau. So the first thing we do is apply the angle sum rule here to break up that sign. Let's first note that this is the sine of 2t minus 2 tau. So we get sine cosine of 2 tau times the angle sum formula we've been using a few times in this chapter already. Gives us the sine of the first angle, 2t, times the cosine of the second angle, negative 2 tau, which cosine is even, so that's a cosine of 2 tau. Then we add cosine of 2t times sine of negative 2 tau, and since sine is odd, we pull that out. Okay, so there's our expansion. Now, because this has both t terms, which are treated as constant when I'm integrating in terms of tau, and tau terms, let me separate out into two integrals. I have a sine of 2t over 2 times the integral from tau equals 0 up to t of a cosine squared of 2 tau, d tau. And then we have minus a cosine of 2t divided by 2 integral from tau equals 0 up to t of cosine times sine of 2 tau. d tau. Now, there's two reasons why I broke it into two integrals. One is that it's a difference, so that I can do it. And two is I want to integrate these two things differently. First, my cosine squared of 2 tau can be broken up using the double angle formula for cosine to write it as a 1 plus cosine of twice the angle, which is 4 tau, divided by 2. On the other side, I have a cosine times a sine, so that gives me a nice u substitution. But of course, we don't use u because that's the unit step function. So we have v equals, you can choose either one. I'll choose the cosine, 2 tau, and then dv in terms of tau would give me a minus 2 sine of 2 tau, d tau. And I have the sine and I have the d tau right here. I just need to divide by a negative 2. Okay, so let me replace my integral up top. Okay, so before I plug my limits, let me just double check here. My v was cosine of 2 tau, and so I had my dv all set except for a negative 1/2, so a negative 2, so I divide by the negative 2, gives me a positive 1/4 on the outside. And then I'm integrating from tau equals 0 to t, so that means v equals 1 up till cosine of 2t. Okay. So now I integrate through. And I might as well factor out common multiple. I get tau plus sine of 4 tau divided by 4 from tau equals 0 to t. And on the other side, I get my v squared over 2 from 1 to cosine of 2t. So I plug in my limits. Sine of 2t divided by 4 times t plus sine of 4t divided by 4, and then I subtract off the 0 component, 0, 0. On the other side, I get cosine of 2t divided by a common 8 times cosine squared of 2t minus 1. Okay, so let me reevaluate what I have right now. I just need to simplify the answer together. So, write that up here. My first term is a t multiple of sine of 2t, all divided by 4. Then my second term has a sine of 2t and a sine of 4t. Now, to keep these things in perspective, let me expand this sine of 4t out using the double angle formula for sine, which is 2 sine of the original angle, 2t, times the cosine of the original angle, 2t. So that gives me a sine of 2t times another sine of 2t. We have a 2 over 4. That'll give me a over 2 here. So plus an 8 sine of 2t squared, and then a cosine of 2t, like that. And on the other side, I have a cosine of 2t times a cosine squared of 2t all over 8 minus 1. And I could combine these cosines and combine the sine squared and cosine squared, but I see something even nicer. Cosine squared minus 1 is the same thing as a minus sine squared of 2t. Using Pythagorean theorem, that cosine squared plus sine squared equals 1. Pythagorean identity in this case, not theorem. Identity. Same thing. And so we can plug that in to get a minus cosine of 2t times sine squared of 2t, all divided by 8. And those last two pieces cancel. There it is.